Okay, guys. Uh, that was auto schedule. Okay. Okay. So we can continue. The thing is, okay. Okay. So guys, I hope my voice is clear. Is my voice clear? Just to check. Anyone? Yeah, good. So the thing is, you would come across these many things in many application, whether it might be thermal power plant or it might be nuclear power plant, whatever it is, you will come across so many things like this. Okay, so many pipelines to condenser, from the condenser to cooling tower, from the cooling tower, so many pipelines can be there. Okay, but in CFD, we cannot take the whole system. Okay, we cannot take the whole system. The thing is, we are supposed to take any one part. For example, if you are interested in studying this particular domain, we are supposed to select the domain, we are supposed to extract the domain separately, and we are supposed to mesh it. Okay, we are supposed to mesh it because CFD is all about numerical method. In numerical method, we are supposed to have mesh elements. Okay, as you rightly told, in finite volume method, values will be computed in the center of the nodes, I mean center of the cells. Okay, so having after meshing it, we can apply boundary condition, we can solve it, and we can get the results. Okay, so this is the step which we usually follow in CFD role. Okay, so this is the thing which we do in CFD thing. Okay, so many things are there. I'll share this presentation with you. Now I'll move on to the software part, guys. Okay, now I'll move on to the software part because if I tell you everything based on the presentation, then definitely you may feel like lost. Okay, I don't want that to happen. So what I'll do is I'll start working on the tool from now. Okay, fine. So guys, now I am going to use a tool called Ansys Fluent. Okay, so commonly known as Ansys Workbench, which I have already opened it. Okay, so in Ansys Fluent you will have so many things. Okay, in Ansys Fluent you will have so many things. So many things in the name. It consists of so many tools. Each and every tool is a separate software. Ansys Workbench is a software holder. Okay, it will have modeling software, it will have analyzing software, it will have post-processing software, it will have programming software, it will have so many things. Okay, but no single person can use all the things. For example, if you are in a CFD, you will use Ansys Fluent. If you are in FEA, you will use Ansys Static Structural Analysis. If you are in turbo machinery, you will be using Ansys CFX. Likewise, each and every company will use separate tools. Now, as I mentioned, I'm going to use Ansys Fluent. Okay, guys, Ansys Fluent is a solver. Okay, Ansys Fluent is a solver. Solver means we are supposed to give it geometry. We are supposed to give it uh, mesh file, everything we are supposed to give it. It will simply solve it. Okay, it will simply solve it. So already I have opened a geometry, I mean already I have opened the space climb which is a geometry modeler. Okay, which is a geometry modeler. Guys, please listen very carefully. Now I'm going to create my own model. I'm going to explain everything in step by step, so that in future you will have some idea about this. Okay, that is very important. This is a geometry modeler which is provided by Ansys, guys. Now what I'm going to do is I'm going to model a heat sinks. Okay, now I'm going to model a heat sinks. Listen very carefully. Now what we are supposed to do is we have something called sketching. Okay, go for sketch mode, make it view normal. Now I'm going for a square. Okay, now I'm going for a square. Square is nothing but a shape, because in order to get a 3D geometry, first we are okay. So in order to create a 3D geometry, first we are supposed to create a 2D geometry. So I'm going to create it for 50 cross 50. Okay, 50 mm cross 50 mm. Here we'll be having a 3D mode. Just click a 3D mode, guys. These things are very important. Okay, so please don't get lost. Now I'm going to pull my 2D to 3D. You have a pull command. So go for pull, just drag it up. It will just get converted into 3D. I'm going to give the bottom plate as 10 mm. Okay. All the side corners are 50 cross 50 and the thickness is 10 mm. Now go for sketch mode, select the top face, make it be normal. Now I'm going to create the fins. Okay. Guys, can anyone tell me what is the application of fins or heat sinks? Where we can use it? I'll sharply end it by 12. So please listen very carefully. Guys, so what is the application of fins?
For rapid cooling purpose.
Very good. What's your name? Fine. So as mentioned, fins is used for rapid cooling. On the other hand, it is used to increase the surface contact area. Okay, so that it can be easily cooled, as rightly told by some student. For demonstration purpose, I am just creating only 4 fins. Okay, guys, listen very carefully. I am just creating 4 fins. So see, we have circles. Now go for pull command. I am just going to pull it for 50 mm. Let's say. Okay, so let's say 50 mm. So I have my fins with the base which is going to get heated. I have cylindrical pin fins. Okay, this is what you'll be reading in your heat and mass transfer. Okay, this is what you'll be reading in your heat and mass transfer. And now this is the solid part. Okay guys, see here it is mentioned as solid. In order to perform a fluid dynamic study or CFD, next what I have to do, can anyone tell me? This is the solid. What I need next?
Apply boundary conditions and
Yeah. Okay. Okay. Please mute it. Okay. So now I have my solid part. Okay. Next thing which I need is fluid part, because guys listen very carefully. See, we have a solid here, and virtually practically we will have a fluid domain there. For example, your room, whatever it is, what happens is heat will get transferred from here to the room, but software cannot automatically assume all these things. So you are supposed to model a domain. Okay, fluid domain. So for that, what we are supposed to do is I'm supposed to create the fluid domain now. So let me do that. So how to do that? So go in the bottom to create a sketch. Okay, now again go for rectangle based on center. So just create a random rectangle. Now what I'm going to do is I'm going to pull it again. This is going to act as a fluid. Okay, so I can pull it to the top. Guys, see what happens is I'll show you. Okay, see, the fluid domain is getting separated from the solid. So this is not a right approach. So what I forgot to do is I forgot to create a separate component. Okay, so go for design, new component. So everything should be separate, so that there will be contact between solid and fluid. That is very important. Okay. Okay, so now I'm going to pull it, guys. So go for pull. I'm just pulling it. See, now the thing is getting merged because this is separate. So I'm going to create it for 70 mm, 20 mm above my heat sinks for cooling. Okay, see guys, so I created a geometry which is a solid. After that, in order to perform fluid dynamic study. I just want to have my fluid volume, so I created my fluid volume. Okay, now I'll name this as fluid. Okay, I'll name this as fluid and save it. Okay, just click save, go for desktop. I'll create a new folder. I'll save it. Okay, see guys, so we have a fluid domain, we have a solid domain. The main thing is my solid and my fluid is getting interfered. Okay, my solid and my fluid is getting interfered. This cannot happen, guys. These steps can be felt like boring, but these things are very important to solve the problem. Okay, only when you know these things you can solve the problem. So please listen very carefully. So next thing what I'm going to do is I'm going to subtract my solid from fluid. Okay, I'm going to subtract my solid from fluid. So combine is the tool name. So I'm going to select this. I don't want to have my solid. Okay, I subtracted it. So you cannot understand all these things now, but definitely at last you'll understand. Okay, see what I meant by subtracting my solid from fluid is when I hide my solid here, you will have this empty space here. See, you will have an empty space here. So it is subtracted. So guys, so this is the fluid domain. This is completely fluid. Okay, I have hidden my solid. So this is completely fluid domain. Okay, so this is where we are supposed to define our boundary conditions, our heat generation, everything. Okay, fine. I'll on my solid here. Now in order to, guys, now my geometry creation part is completed. I have created my solid, I have created my fluid. Next I'm supposed to define the boundary conditions. So boundary conditions is nothing but I want to define which is the inlet, by which way the air will enter, by which way the air will go out, what are the heat generation boundary conditions, everything I want to mention. Okay, so everything we want to mention. Okay, so how to do that? So in space climb, that is named as groups. Okay, in space climb, that is named as group. So now I want to define this phase as a inlet. So create group. Now right click, rename inlet. I'll do it quickly. And all the other phases, okay, all these things are supposed to be adiabatic. No heat transfer will happen. Okay, no heat transfer will happen. So I'll select all these things and I'll name that as adiabatic. Adiabatic means no heat transfer will take place. This is going to be outlet. So air comes via inlet, air goes via outlet. Now I'll hide my fluid. Okay, I want to see my solid. Okay, now so these areas, these are the areas which is in contact with the fluid. So these are the areas in which heat transfer will take place. So select all those, go for create group. In the group name, create the naming as heat transfer area, just for reference. Okay, heat transfer area. So guys, so what are the boundary conditions we have? Now I will see this. See, we have inlet, we have adiabatic, we have outlet, we have heat transfer area. Okay, so all the walls, all the boundary conditions are named. Okay, with this you can save it, guys. So far any doubts? Guys, so far any doubts? I am very happy that 46 students are here. These things are very important when you want to get a job in
No,
industry.
sir.
Fine. So far clear. So this part, okay. So this part. So far we have created a geometry, we have created a fluid domain, we have created a naming section. So till this, it is known as geometry cleanup. Okay. In CFD, it is known as geometry cleanup or pre-processing. Okay. Only when your pre-processing is good, your CFD solution can be trusted. Else your CFD solution is just a garbage. Okay, it cannot be used. So we have created all these things properly, so we can close it. We can go for next step. See, so it is not updated here. So if it shows question mark, it is not updated here. So give update. Okay, I'll save it now. Okay, so I have saved it. Now I'll load the geometry here. The geometry is not loaded here. So go for import geometry, browse, go to the folder, design one, give OK. So it will show the tick mark. If the tick mark is there, your geometry is loaded. Okay, now right click it. Okay, right click it, transfer data to new isom cfd. Okay, because as I mentioned guys, see here, see here. So what happens is you have a geometry. So this part we have created. Next, what we are supposed to do is we are supposed to create a mesh. Okay, so far we have completed till this. Next, we are supposed to create a meshing. Okay, so now I'm moving on to the meshing part. Okay, listen very carefully. This is also very much important, guys. Okay, I'm closing the space climb window. So guys, so this software is called isom cfd. It may look like your AutoCAD, very basic software, but companies, even companies like ANSYS, very big, very big companies. Lot of companies are there, like Data Patterns are there, Cognizant, so many companies. Okay, they use isom cfd for their cfd machine, because this is one of the robust tool to create a cfd mesh. I'll tell you very basic procedure. Okay, when you follow these procedures, definitely you can create a mesh on isom cfd. So listen very carefully. It is loading up the geometry. Okay, it is loading up the geometry. So let us give some time. Okay, see guys, the geometry is loaded. Okay, the geometry is loaded. It is like a 2D wireframe. So first we are supposed to go for geometry, switch on the surface, switch on the surface on the top. See, so this is how your thing will be imported to the isom cfd, because meshing is the very computationally important thing. Sir, we have input limits and units, or no need to run this application during drawing. Muhammad Abdul Munir, sorry, I'm not getting you. Good. Being a second year student, you are asking some doubts. It is appreciable. What's your doubt actually?
Sir, in CAD, uh, we input the units, limits and units, no, sir, while
Oh,
drawing.
fine, fine, fine. Very good,
Yes,
very
sir.
good. Actually, in CFD, all the units will be considered in meters. See, in the bottom, it will be mentioned.
Yes, sir.
See, it will be mentioned in meters. So there is no need for us to export the things or define all those things. All these things are automated, but we can do. But that is not needed. Okay, fine. Now I'm just
Thank
switching
you.
on the surface to
Thank you.
transparency. Yeah. So this is how your model will look like. Now what I'm going to do is I'm going to run the topology. Topology means, guys, without the proper topology, you will not get your CFD simulation done. Okay. The thing is, topology is nothing but information should be carried out from the fluid to the solid. Again, from the solid to the fluid. Okay. So in order to be these things to be clear, we are supposed to do something called topology cleanup. Okay, or topology sharing. So in order to do that, ISM CFD provides us the automated tool. Just go for topology cleanup. Just give apply. See, it is showing red color. Red color means the thing is shared between two surface. It is good. But in the bottom we have blue color, which means there is a T junction. The same edge is shared by three surface. Sometimes it happens. Okay. Fine. So now the thing is clear, guys. If there is some yellow surface, for example, if you delete any one of the boundary, it will show you yellow surface. Okay. Yellow surface means surface is missing. Geometry is not good. Okay. You cannot perform a CFD simulation with this kind of stuff. Okay. So if all the thing is red color, all the edges are blue in color, then you can proceed with your CFD simulation. Okay, CFD simulation. Now I'm going to create a mesh, guys. Okay, I'm going to create a mesh. See, in the bottom you will have inlet, outlet, heat transfer area, adiabatic area. Everything will be mentioned here. Now I'm going to do a thing. Fine. So this is just a check, some advanced level thing. You can learn it in future. Okay. Fine. Now I'm going to define the boundary conditions, which is solid, which is fluid. Already I have defined that in space climb, guys. But ISM CFD, we have to create that separately. Okay, we have to create that separately. ISM CFD will not get that detail from space climb, only the detail. Okay, now go for create body. First body is fluid. First body is fluid. Now go here, select any 2 points. See, the fluid material point is created. I hope it is visible. Okay, fluid material point is created. Now what I'll do is I'll hide the adiabatic area. Now my solid portion is visible. Now go for body. Now I'm going to define this as solid. Okay, now I'm going to define this as solid. So see, my solid boundary point is created. I have my solid, I have my fluid. You can uncheck it now. Okay, so guys, see, first we created a geometry, we created the fluid domain, we named the boundary conditions, we exported all the things to ISM CFD for meshing. Now we have performed topology cleanup, we have given the boundary conditions, like which is fluid, which is solid. Okay, now I'm going to do the very important thing, which is creating a mesh. Okay, so go for mesh tab, go for global mesh setup. Okay, go for global mesh setup. Before that, I just want to see the minimum length. Okay, because if you want to define the length, okay, you are supposed to measure the distance. It is like 0.009, so you can give 0.005. See, guys, um, I created all the model in mm, and when all these things got exported to ISM CFD, everything got converted to meters. So the values will be very fine. So based on that, we are supposed to give our mesh setting. So when I check the minimum dimension here, it is 0.009 meter. Okay, 0.009 meter. So I can give like 0.005 as my maximum element size. Okay, maximum element size. So I have defined my size. Now I'm supposed to create my mesh. So go for compute mesh. See, here in meshing method we have octree, Delaunay, advancing front fluid meshing. So many things are there, but with this time constriction, we cannot go in detail in all these things. So I'm going for robust octree. If we have time, I'll explain all those things. Okay, compute. Okay, the see, guys, so the mesh is good, decent mesh, but I'm not sure about my inlet part, which is solid part. So in order to see the inlet part, I'll switch on my volumes. So go for mesh, show cut plane. Oh, okay, my cut plane is not properly aligned. So I'll do one thing. Go to the bottom, I'll move it. Okay, okay, guys. See, I'll hide my surface. See, This is good mesh or bad mesh? Can anyone tell me? Guys, I'm asking you. Is this good mesh or bad mesh? Looks beautiful. So sad. No.
Good
Bad
mesh,
mesh.
good mesh.
No, it's a bad mesh. Okay. Why I'm telling bad mesh is it failed to capture my geometry. No, the good mesh will capture your geometry clearly. See, your cylinder is not looking like a cylinder. It look like something distorted. Okay. So this mesh cannot be used to perform a good CFD simulation. But this is our initial mesh. Okay. This is our initial mesh. So next, what I am supposed to do? Go for a global mesh setup. I will scale it down. Okay, I will scale it down. So there is no single way to show that to create your mesh properly in the first thing itself. It will take so many iterations. Now go for compute, replace. It's going to take some more time. 2 lakhs, 3 lakhs, 5 lakhs, 6 lakhs, 7 lakhs, 8 lakhs, 9 lakhs, 1 million. Now we have 1 million. It's like 10 lakh mesh. Definitely, this count is huge. So my geometry would be captured very good. Let's check it. Okay, guys. Okay. So the mesh is so fine. Now let us check it. Okay. So go for show cut plane. Show the volume mesh. See, guys. So now the geometry is captured nicely. Okay. So the geometry is captured nicely. I can do one thing. I'll hide my volume. I'll hide all of my surface. I will go for heat transfer area alone. I will, okay, adiabatic. See, so even now the meshes scores not that much fine around my heat transfer area. Okay, so the surface is not captured that much smoothly, but this is fine, guys. Okay, because if we further reduce our mesh count, what will happen is it will take so much time. For this mesh we have around 10 lakh elements. If we further move on, solution time will be very high. So now what I'm going to do is I'm going to follow another principle. Okay, I'm going to use another strategy to smooth the mesh. So let's see how to do that. I'll delete all the volume mesh. Okay, guys, our mesh is divided into surface mesh. You can ask me what is surface mesh. I'll tell you. If I hide the inlet, hide the volume mesh. See, so this is the surface mesh. So the surface mesh will be on the surface of your geometry. Okay, surface of your geometry. So if this is good, your volume mesh will be good. So what I am going to do is I am going to delete all my volume mesh. Guys, please mute. Yeah. So what I'm going to do is I'm going to delete all of my volume mesh and I'm going to smooth my surface mesh. Okay, this is one of the procedure to create a good mesh. Okay, so go for delete volume mesh all. Okay, see, guys, all of our volume mesh is deleted. Okay, I made a small mistake. I deleted all the mesh. Fine. Okay, so it is creating a mesh. It is faster than before. Okay, so the mesh is generated. Now, as a usual practice, what we do in industry is we will delete the volume mesh. Okay, so select the volume mesh, just apply. See guys, so the volume mesh is completely deleted. Okay, if I go through the inlet, there will be no volume mesh. Now I want to smooth my surface mesh. Okay, so only then you can generate a good volume mesh. So in order to smooth it, I just want to check the quality. So go for quality, click apply. The minimum quality is 0.3. This is fine. But what happens is when we generate a volume mesh, this will again go down. So I will go for smooth mesh. I need the quality of zero point 0.6. Okay guys, so zero point 0.6, that is very high quality. I want the quality of zero point 0.6. Automatically it will take care. See, I have a zero point 0.5 quality. So this is so good. So what we can do is, I'm just going to create my volume mesh. So go for compute mesh. Now guys, first I used Octree. Now I'm going to use Delune. Okay. Now I'm going to use Delune. The thing is, if you don't have any mesh, then Octree works fine. If you have a surface mesh, then Delune works fine. Okay. So I'm going for Delune. Click compute. So let us give some time. Okay, it's done. It's super quick. Okay, Deluna is super quick. Now I'll go for mesh, cut plane, show. I'll click on volumes. I'll hide the surface. Uh, I'll manage my cut plane. Okay, guys, listen very carefully. I'm just moving it to check the quality. See, even now the cells are a bit distorted. I'll move it. Okay, see guys, at the middle of the cylinder, my boundaries are exactly captured. Okay, so this is the quality of very good mesh. Okay, this is sufficient for me. Okay, so I have created my mesh, guys. Now, see, first we created the geometry, we created the fluid domain, we created the name, we brought that into ISM CFD, we created the mesh. Okay, now I want to export this to the Fluent. Okay, as I mentioned, Fluent is a solver, CFD solver. Okay, so guys, any doubt so far? You can ask me now. Any doubt so far? I'm just going. So if you have any queries, you can ask me now. I'll give you 2 minutes because our important thing is completed. We have created a good quality mesh. Next, we are going for answers fluent. So before that, if you have any queries, you can ask me now. Guys, I'll give you 2 minutes. You can ask me doubts now. Okay. Sir, can't we adjust the mesh thickness? Abdul Munir, here there is no need to adjust mesh thickness. Okay, the mesh thickness doesn't come to play here. Okay, so it is not thing here because first we used Octree. Next we use Deluni. Okay, automatically it will optimize the things, so that's not a big issue. So any other doubts, guys? Further, we can refine a mesh for around 20 lakhs, but that is not a requirement here. Okay. See, first we created geometry. Next, we performed some things, naming and all. We exported the things to ISM CFD. Here, we created a good mesh. Okay. In the mesh, we have so many things, guys. If you have a note, please make a note. Majorly, we have two kind of mesh. One is tet mesh, another one is hex mesh. I'll even annotate here. See, one mesh is tet mesh, another one is hex mesh. For all geometry we can create tet mesh, but in order to create a hex mesh it requires specific concept called blocking. Okay, requires specific concept called blocking. It cannot be done to all geometry. Only experts can do that. Okay, that option is available here. See, blocking is there. It will take so much time in blocking. As Munir asked, mesh thickness can be optimized, so many things can be done, but that is not applicable for tet mesh. Okay, that is not applicable for tet mesh. Guys, I hope everyone is clear with this. Okay, so next we can move on to fluent solver. Okay, guys, ISM CFD is a general purpose measure. Not only it suppose answers fluent, it suppose many things. Okay, it suppose many things. So I want to create a mesh for answers fluent. Okay, so go for output mesh, go for select solver. Make sure, see, so many solvers we have, so many solvers we have. As a students, definitely you may not come across all these, but definitely you are supposed to be strong in all these things. Okay, I am going to create answers. I am going to click answers fluent, go for boundary conditions, volume. So what is fluid, what is solid? So this is my fluid. Just telling the software which is solid, which is fluid. Okay, now go for surface. Which one is inlet? Guys, I'm going to define velocity inlet. Okay, because even if you have a fan, it will be considered as a velocity inlet. Outlet will be pressure outlet. I'll tell you why.
5 मिनट में मिला रहा कार्ड फॉर्म फिलअप करे पीछे गए मैनेजर को दिए वाइस मैनेजर को दिए
Okay, fine. So pressure outlet and adiabatic, it is nothing but a wall. Okay, it is nothing but a wall. In two-sided, we have heat transfer area. It is better to leave that, or else you can define that too as a wall. Okay, that's all, guys. Just check mixed, because that sometimes it will give you error. So now that is not a problem. So I'm accepting it. Okay, now go for right input. It will ask you something. Give save, select a mesh. See, this is the answers fluent exporter. Okay, I want the mesh to be in 3D. I don't want to scale my mesh. Give done. There is some question. I'll tell you. Is there any option to use combination of polygon? Yeah, definitely, Shakib. The thing is a bit advanced, okay? Because students are from second and third year, so I have not gone into polygonal meshing. But we have something called polyhedral meshing, which is in ANSYS Fluent, which is in star CCM. That is the main objective of polygon is to reduce the mesh count. If you use tet mesh, if you use hex mesh, the count will be like 10 lakhs, 20 lakhs, even in some case 1 crore, 2 crore. I have created mesh of that much volume. In that case, the problem will solve for 2 days, 3 days, 4 days. After 4 days, if the solution is wrong, again I have to wait for 3 more days. So in such case, we will go for polyhedral measure. It will bring down the mesh count by 50%. If the mesh is like 1 crore, it will bring it down by 50 lakhs. Just you can see the power of polyhedral meshing. Very good. So you can use it, but in this case, I'm not using that. Okay. See, guys, in the bottom, we have something called done with translation. So the mesh is converted, which is supported by ANSYS Fluent. So our part is done here. I'm going for ANSYS Workbench. Just make sure you have a tick mark here so that everything is fine. Now right click it, go for new, go for ANSYS Fluent. Guys, I hope you can see the steps. First geometry, next to meshing, next to solving, next to result viewing. Okay, now go for setup. I will close my meshing here. I want 3D. I don't want double precision, it will take so much time. I want parallel processing for efficient solving. Give OK. Guys, why I am doing everything practically is anybody can read the presentation. Okay, I have so many presentations. If you want to see, I can show you. See, I have so many presentations for a complete answers thing. Okay, all the products and answers, I have presentations. But the thing is, if I simply read the presentation, definitely nobody will understand anything. That is why I'm doing everything practically, parallelly explaining the steps which is involved in CFD. Okay, so that definitely after the session, if somebody asks you the steps in CFD, and anyone attending the session can answer. Okay, I hope that is possible. Okay, that's why I'm taking this much time and this much effort. So please listen very carefully. Guys, answers fluent will read the mesh. See, it created the mesh. So many color codings are there in CFD, guys. Okay, red color indicates inlet, blue color indicates outlet. So many things are there. In this time, it is difficult to explain all the color codings, but I'll tell you one by one. Okay, so this is the answers fluent, guys. Okay, as you can see, you can imagine like you are working in a very big software, so many stuffs, small output window, so many input thing. Okay, see, input is more here, output is very less here, because answers fluent, it is like a programmer. Okay, we are supposed to give so many inputs so that we will get a proper output. So once you enter the answers fluent stuff, first thing we are supposed to do is we are supposed to check it. Okay, it shows no error, it means so far we have done a perfect job. If you check a mesh, if it shows some problem, it will show some red color indications and all, then your mesh is problematic. You're supposed to check everything from first. Okay, now I'm going for model, I'm going to switch on energy, I'm going to solve for heat transfer equation. Okay, this is the important thing which we want to do. I'm supposed to solve it for energy equation, I'm supposed to solve it for turbulence. Okay, I hope in your from your second year, I would study fluid mechanics. Definitely, you know what is meant by laminar or turbulent and all. Here, I am going to solve for turbulent boundary condition. I am going to use K omega SST model. That is a leading turbulence model. Okay. I will share some of the PPTs with Salman Khan sir after this presentation. You can go through that PPT, everything will be in detail there. So after attending the session, when you go through that PDF, you will understand the many important things. Okay, so what is SST, where you use it, everything will be detailed. So I'm using K omega SST model. Now go for materials, guys. So fluid is here, solid is aluminum here, it is fine. Go for cell zone condition, we can skip it now. So this is important. Boundary condition. Okay, we are supposed to give the inlet, so click the inlet velocity, edit. So let's say I can give, for example, if you have a fan in the inlet, can give 2 meter per second, 3 meters per second. I'm giving 2.5 meter per second. So that is the inlet velocity. Outlet, usually it will be zero pressure gradient because it is exposed to atmosphere, it is zero. Now heat transfer area, guys, the very important thing which you do here is give concentration to heat transfer area. It should be coupled. Okay, it should be coupled. Thermal, see, it should be coupled. Only if it is coupled, heat transfer will take place. Okay, if it is not coupled or something like that, heat transfer will not take place. So only just make sure that it is coupled. Okay, Now they have given inlet 2.5 meter per second, outlet pressure outlet which is exposed to atmosphere, and the walls it is coupled. Okay. Now I am supposed to give heat generation. Okay, because in the solid heat is getting generated. So go for edit. Sure, Shahid. So go for source terms. Okay, go for source terms. I am going to define heat generation constant. I am just going to give 1000 or 10,000 watt per meter cube because our model is so small. So only when you give a big value, it will be considered here, because here it is like point 0001. Okay, so we are defining for the whole meter, watt per meter cube. So only when you define higher value, it will be considered in the small scale models. So define. Okay, guys. So I have defined the boundary condition. I have defined the heat generation. Now I am going for methods. I am going to use simple scheme here. So many schemes are there, but now I am going to use simple scheme. It will take less time, but the solution will not be that much accurate, but that is sufficient. Okay. Now I am going for initialization. Initialize. Initialization is nothing but the software will check for errors. Okay, if the error is less than some like 10 to the power minus 6, our solution setup is correct. If it is not, then we are supposed to remesh it. We are supposed to do so many things. Okay, but see, we got 10 to the power minus 7. Our setups is error free. Okay, we can proceed. Okay, guys, the hybrid initialization is successfully done. Now I am going to run the calculation. I am going to run the calculation. So I am going to run it for 1000 iterations. Okay, guys, from here you can take a break of 5 minutes. Okay, from here you can take a break of 5 minutes. See, I will run it now. Just calculate. It will take some time. Okay, in order at least if we cross some 100 iteration, we will be able to see the results clearly. Okay, so for that at least it will take 5 minutes. See, our solution is getting started. I want to explain. See, so far we have seen many important things, but very important things are after this. Only when you witness the result, you can learn so many things. Okay, so it is starting to get run. Okay, take a break of 5 minutes. Be here by sharp 11:40 or 11:46. Okay, we will end our meeting by sharp 11:50. Okay. Okay, guys, please take a break of 5 minutes. Yes, guys, if you have any queries, you can ask me. Okay, please have some water and come back.